Solutions of differential equations. So remember that a differential equation is going to relate a function with its derivative. So when we're looking at something that has an equation that involves the derivative of an unknown function, the unknown is not a number, but its own function. So when we solve a differential equation, we are finding a function that will satisfy our differential equation. So we expect our solution to be in function form. There are two ways that we solve differential equations. The first is if you have a possible solution, you can check to see if it's a solution by using some techniques from calculus and differentiation along with some algebra. Now, this may seem a little odd that you would be given a solution to check, but one of the strategies that we use with differential equations is guess and check. We don't have enough background information on differential equations yet to start guessing the form and type of solutions there will be, but we can certainly practice looking at whether or not something is a solution so that when we get to the point where we can come up with good guesses, we can check to see if those are solutions. The other scenario for solving a differential equation will be to find a solution using algebra, integration, and possibly initial conditions to find either a general or specific solution. There are other techniques to solving differential equations, but those are more advanced than what we will get to in this course. So there's two methods, and the method you're going to use depends on what type of question you have. So we're going to begin by looking at questions that ask us to check possible solutions to see if they are indeed a solution to our differential equation. Let's look at an example. Example 1. Consider the differential equation dp dt equals 2p. So the derivative of p is equal to 2p. We want to determine if p equals ce to the 2t is a solution. So remember, by looking at our differential equation here, p is going to be our dependent variable and t is going to be our independent variable. And we can tell that from the derivative. The dependent variable is always on top and the independent variable is always on the bottom. So what that tells me is that c is just some constant. So we'll treat that like a constant. So to find out if this is a solution, we need to have p to be able to plug in here, which we already have, but we also need dp dt. So the first step here is going to be to find the derivative of this function. So if we take the derivative of ce to the 2t, remember that when you take the derivative of an e term that has a constant in the power, that constant comes out front. So that's going to give me 2ce to the 2t. That's the derivative of my possible solution. So now what I need to do is I need to go back to my differential equation and see if the equality holds. So on the left side, it says I have my derivative. So I just found that. So I have 2ce to the 2t. And I want to know, does that equal 2 times p? So 2 times p is 2 times, and then I fill in what p is, which is ce to the 2t. So the question is, are these equal? And the answer is yes. They say the same exact thing, 2ce to the 2t. So yes, this is a solution. Now, that doesn't mean that there aren't other solutions to this. We don't know. All we know is that we checked the proposed solution and it satisfies our differential equation. So that's how we start to check these. Let's try another one. Example 2. Consider the differential equation y prime minus 2y equals 0. Determine if y equals e to the negative 2x is a solution. So there's slightly different notation here. We're using y prime instead of dy dx. I know that y is my dependent variable because it's y prime, and that x is my independent variable because my solution has y as a function of x. So I have my y, which I need as part of my check here, but I also need a y prime. So the first thing I need to do is compute the derivative of my possible solution. So again, if I take the derivative of an e term, then the constant will come out front. So here I'm going to get negative 2e to the negative 2x. So again, I have to plug in all the pieces and see if the equality is true or not. So I'm going to do y prime first, so negative 2e to the negative 2x minus 2 times y, so e to the negative 2x, and I want to know, does that equal 0? Now, it's a little deceptive here because you see two terms, they look the same, it looks like they could easily cancel out, but they don't. So negative 2e to the negative 2x minus 2e to the negative 2x is minus 4e to the negative 2x, which does not equal 0. So no, this is not a solution. If my differential equation had been y prime plus 2y, those would have canceled and it would have been a solution. But since it was minus, it didn't work out. So that is not a solution. So keep in mind when you're checking solutions, not all of them will work. So you have to be careful with your algebra and plug in carefully. Let's look at another problem. Example 3. Find the value of a so that the differential equation y prime minus xy minus 4x equals 0 has a solution of the form y of x equals a plus be to the x squared over 2 for any constant b. So notice here that this differential equation is certainly more advanced than the ones we've been looking at. The good news is we didn't have to set it up and we don't need to solve it. We just need to check for a solution that satisfies these conditions. So again, we see the derivative, y prime, and we also see a y. So we're relating the derivative and the function in the same equation. So in order to plug things in and work through this algebraically, I need to figure out what y prime is. I have my y function, so I'm going to take the derivative of that. Now when I do this, it's important to remember that my independent variable here is x. So when I take the derivative, I'm keeping in mind where the x is to figure this out. The derivative of a is going to be 0 because it's a constant. And so for my e term, when you take the derivative of e to something complicated, which is what we have here, we get the same thing back, so be to the x squared over 2, times the derivative of the power. So the derivative of x squared over 2 is x. So I'm going to write that in front. So the derivative of my function looks like this. And again, I was using the chain rule to find that. And now I need to plug in all the pieces to see what I can figure out. So my y prime comes first. So I have x be to the x squared over 2 minus x times y. So I'm going to plug in my y equation here. A plus be to the x squared over 2 minus 4x equals 0. So remember here, we're plugging in for y because those are the things that are dictating our differential equation because it's y that has the derivative and the function in the problem. Remember, we're trying to determine the value of a that would make this true for any value of b. So we're going to do a little simplifying here to see what shakes out. I'm going to distribute this minus x through the parenthesis. So we have x be to the x squared over 2 minus xa minus x be to the x squared over 2 minus 4x equals 0. So something interesting is happening here. I want you to look at the e term. We have a positive xbe term and a negative xbe term. So those are going to cancel out, which leaves me with negative xa minus 4x equals 0. So remember, I'm trying to solve for a here. So I can bring the first term over to the right. I have negative 4x equals xa. So I know that a has to equal negative 4 if I solve this. Divide both sides by x. So when x is canceled out, I'm left with a equals negative 4. And so when a equals negative 4, I have a solution to this problem of the form a plus be to the x squared over 2 for any b, because that b is going to cancel out as part of the process. So I'm able to solve for a. So when you're looking to solve for a constant that satisfies a differential equation, the key pieces are finding the derivative and the function and plugging them in, and then using algebra to determine whatever the condition is that you are trying to solve for. Let's look at another example. Example 4. Find the values of the table below given that dp dt equals 0.2p. So we're given the differential equation that models this table, and I want you to notice that we're also given a starting value. So what we need to do is pair what we know about derivatives and what we know about differential equations to figure out the other values. So at time equals 0, my p is 36. So if I plug in 36 into my differential equation, dp dt equals 0.2 times 36, if I multiply those together, I get that my derivative is 7.2. So remember, the derivative tells us how much a function changes within 1 unit of my independent variable. So to go from 0 to 1, I expect my function to change by 7.2, which means that I can add that 7.2 to 36 because that gives me the correct rate of change. So when I add it to the 36, I get 43.2. Now we know from Calculus 1, if we were to approximate the derivative on the table, we would do the change in p over the change in t, and that would give us a derivative estimation of 7.2, and that's what we have. So how do we go from 1 to 2? Well, again, we need to figure out how much our function changes based on the current dependent value. So 0.2 times 43.2, that's going to give us 8.64. So again, since the change is positive, I'm going to add that to 43.2. So when I add that to 43.2, I'm going to get 51.84 as my value at 2. Again, if I want to move one more unit to the right to 3, I need to look at the rate of change at the current value. So 0.2 times 51.84. When I multiply those together, that's going to give me a change of 10.368. And again, since that's positive, I'm going to add that to my 51.84, giving me 62.208. If I want to go from 3 to 4, I need to figure out how much I changed at that level. So 0.2 times 62.208. When I multiply those together, I get a change of 12.4416. Again, I can see this is increasing. I can see that this is positive, so I'm going to add it to my 62.208, and I'm going to get 74.6496. And then finally, to go from 4 to 5, I need to do one last calculation to figure out how much I'm changing, again, approximated by the derivative. So I do 0.02 times 74.6496. And I get a change of 14.92992. So 14.92992. And so I add that to my 74.6496, and I get my final approximation of 89.57952. So to fill in this table, I need to look at the derivative of how much I changed from one point to the next, which I can find by using my differential equation. And then I need to keep plugging in my new dependent value to figure out how much my function is changing. And then I can fill in down the table. So let's look at another example. For the next set of problems, we are going to now try to find a solution for our differential equation. So we're not going to be testing if a solution is a solution. Instead, we're going to use what we know and our techniques to find a solution for our differential equation. Example 5. Find a general solution for dy dt, the derivative of y with respect to t, equals 5t cubed. So what do we mean by a general solution? So when we do our process here to solve this differential equation, we're going to have one unknown, which you'll see as we go. A general solution leaves that unknown as an unknown. If we had some sort of initial condition, which we'll look at in later problems, we would be able to find a specific solution. So here we call it a general solution because we don't have any initial data. So how do we start with this? So consider this derivative dy dt. Our dependent variable is going to be y, that's the value on top here, and our independent variable will be t. And so in order to solve these, we need a function that's y equals some function of t. The way we arrive at this is by separating out our derivative, much like we did when we were doing integration techniques earlier in the term. So what we have to do here is we're going to multiply the dt up, giving me dy equals 5t cubed dt. So what I need to check here now is that my function matches my integrand operator. So I have 5t cubed dt. Those match. So my equation is set up for solving now. If I had 5y cubed, I would need to bring it to the other side so that the y's were with the dy. So now that I have that separated, the operators, the dy and the dt, I can integrate both sides. So sometimes my integration is straightforward. Sometimes I'll have to use a technique like integration by parts or integration by substitution. But typically these are going to start off with integration techniques that are from our basics chart. So on the left-hand side, we have the integral of dy. So remember, there's an invisible 1 there. There's always an invisible 1. So when we integrate that function, that 1 is going to pick up the variable of integration, which is y. Now on the right-hand side, when we integrate 5t cubed, we're going to add 1 to the power and divide by the new power. So when we integrate, we have a plus c. We don't need the plus c on both sides because we can combine them to get a general c. So the convention is to put the plus c on the side with the independent variable, because the goal is always going to be to solve for y. So if y was more complicated than just y, we would have to use algebra to solve it into a y equals. But here, fortunately for us, it's already y equals. So here we have found a general solution to our differential equation. Now we could check that solution like we were doing in previous problems by plugging in our derivative and make sure it equals 5t cubed, which it will. As a reminder, when you take the derivative of c, that'll be 0 because it's a constant. And this is a general solution because c can take on any value. right? So C could be 5, C could be 10, C could be 100, and it would still satisfy this differential equation. We don't have any initial information to solve for a specific C. Also, just as a point of clarification, I just want to remind you that y is a function of t, so even though we're writing it as y equals, it's actually y of t equals 5t to the 4th over 4 plus c. We're going to be just doing y equals, but remember that y is a function of t, so if you see it written as y of t, you know that it's just a writing convention and not anything different. Let's try solving another one. Example 6. Find a general solution for dy dt equals negative y squared. So again, we start by isolating our derivative. It's already isolated. And then we're going to multiply up the dt. So we have dy equals negative y squared dt. So here we see that we have a mismatch. The y term is with the dt, and we need that y term to be with the dy in order to be able to integrate. So we're going to divide out this whole term in order to get this to match up. So on the left-hand side, I have negative 1 over y squared dy equals, and then on the right-hand side, I now just have a dt. So I'm going to do one more step to rewrite this. I'm going to bring that y term up from the denominator algebraically so I can use my integration techniques. So that's going to give me negative y to the negative 2 dy equals dt. So again, when you bring a term up from the denominator, you need to change the sign of the power. So it was positive, so now it's negative. So now the y's are with the dy. They're in an algebraic form that I can integrate them. So I'm going to integrate both sides here. So on the left-hand side, I'm going to add 1 to the power and divide by the new power. So that's going to give me negative y to the negative 1 divided by negative 1, and I'll simplify that in a moment, equals t plus c. So on the right-hand side, there's a 1 dt, so that becomes t when integrated, and I put my plus c with my independent variable. So on the left-hand side, the negatives are going to cancel here, and I'm going to resimplify that into 1 over y equals t plus c. So remember, y is my dependent variable. So that's what I want to be solving for. My final equation should say y equals. So I'm going to do a little algebra and reciprocals here. So I'm going to get y equals 1 over t plus c. So solving for y gives me my final solution here to my differential equation. One of the key things that happened here was that I had to bring the y terms over to the dy before I could integrate. So again, any variable has to match the integrand operator. So if you have y's, they have to go with dy. If you have t's, they have to go with dt's. If you have p's, they have to go with dp's. If you have m's, they have to go with dm's. You have to make sure those match up in order to be able to integrate. So now we have our general solution, and again, it's general because that c could take on any value. Let's look at another problem. Example 7. Suppose that left alone, the deer population in a particular state increases at a continuous rate of 30% per year. Suppose that deer are also hunted at a constant rate of 6,000 deer per year. Set up a differential equation to model this population. If there are initially 14,000 deer, find a solution to the differential equation. So we already set up this differential equation in a previous section, but we'll do that work again. And then once we've set it up, we'll solve it, and we'll be able to find a particular solution because we have an initial condition. So the first step is to set up a differential equation that represents what's happening in this population. So I'm just going to define my variables over here. So P is the deer population. T is going to be time in years. And I know that the population at times 0 is 14,000. So those are things I just want to write down before I even start so that I'm clear about what all my variables mean and the information I have. So for my differential equation, the rate at which my population is changing is 30% per year, so 0.30p. And then I'm also hunting out 6,000 deer per year. So that's going to be a minus because that's the amount going out, right? So this is the amount that we are growing, but this is the amount that we are declining, right? So when you're losing something, you have to subtract it. So we have our differential equation here, and we want to solve this so that we have p as a function of t. So p equals something in terms of t. So our strategy again is to first split up our operators. So dp equals 0.30p minus 6,000 dt. So we have a mismatch here because my p term is with the dt, and I need it to be with the dp. So I need to bring that term to the other side, but I need to be really careful. So remember, algebraically, I cannot separate the 0.30p and the 6,000. Those have to come over together. So I have 1 over 0.30p minus 6,000 dp equals dt. So now the p's are with the dp, so I can integrate both sides. Now the right hand side is much easier to integrate, right? The right hand side is just going to become t plus c. But on the left hand side, I'm going to have to use integration by substitution in order to solve this. So I'm going to do my substitution over here. So here I notice that my denominator is where this p is. So I'm going to let u equal my denominator. So 0.30p minus 6,000. So that means my du is going to equal 0.30 dp. So when I look at setting this up in terms of substitution, I have 1 over u, but now I don't have a 0.30 dp, so I'm going to divide both sides by 0.30 so that I can substitute in directly for dp. So times 1 over 0.30 du equals integral of dt. So now these are both in forms that I can integrate. So on the left hand side, I have 1 over 0.30, that's a constant, of the natural log of the absolute value of u, right? So 1 over u integrates into the natural log. And then on the right, I have t plus c. Now remember, I don't want a u in my final equation. I want a p because that's what I'm trying to solve for here. So I have 1 over 0.30 natural log absolute value. I'm going to substitute back in. So 0.30p minus 6,000 equals t plus c. So I've solved the integral part of this problem, but remember, I want to have p equals, right? So I have to do some algebra in order to make this happen. So in order to solve for p, the first thing I'm going to do is I'm going to multiply both sides by 0.30 to deal with this constant here. So multiplying gives me the natural log of 0.30p minus 6,000 equals 0.30t plus c. Now you may be thinking, should it be 0.30 times c? Well, c just represents a generic constant. So c actually absorbs anything we do to it until we solve for it. So 0.30 times c is just another constant that we can call c. So now, in order to get rid of the natural log, I need to exponentiate both sides. So 0.30p minus 6,000 equals e to the 0.30t plus c. Now, something that happens here quite often is an algebra rule that you may or may not remember. So let's look at the e term for a minute. We can rewrite this as e to the 0.30t times e to the c, because when they have the same base, you add their powers. So we're going in the opposite direction. And the reason why we're doing that is because e to the c, remember c is just some number, is just another number. So this itself we can just call c. So that means we can rewrite our equation as 0.30p minus 6,000 equals c e to the 0.30t. We can now add 6,000 to both sides. So 0.30p equals c e to the 0.30t plus 6,000. And then last but not least, we need to divide both sides by 0.3. So p equals c e to the 0.30t. So again, when you divide c by 0.30, it just gets absorbed, plus 20,000. So now we have what's called our general solution. We had to do a lot of work in algebra and integration to get there, but we have a general solution. However, we had an initial condition here. So remember, there were initially 14,000 deer, right? So that means if we plug in a 0 for t, we can solve for c. So p of 0 equals c e to the 0 plus 20,000. We know that that will have to equal 14,000. Remember, e to the 0 is 1. So we have c plus 20,000 equals 14,000, which tells me that c has to equal negative 6,000. So my true and final answer, after all is said and done, is going to be p, or p of t, equals negative 6,000 e to the 0.30t plus 20,000. If I wanted to check to make sure I did all my algebra right, I could go back to my first methods where I was looking at checking a solution to make sure that it worked, right? By taking the derivative and plugging things in the right place and making sure that the equality holds. So this problem is a full differential equation problem. We started by setting up our differential equation using the information given. Then we had to use our integration techniques to figure out what our p and our t side looked like. And then we used algebra to solve for a general solution. Then we used our initial data to find a specific solution. So this one is definitely one of the harder types where we have to walk through every single step. However, when we're talking about integration in order to solve differential equations, we do have to use those integration techniques that we've been looking at throughout the term.